Imagine asking an AI to research a complex topic. It starts searching, reading documents, and trying to keep track of everything. But as the conversation stretches, it starts losing the thread. It forgets which documents it already parsed, which clues actually matter, and which ones to discard. Why? Because most AI research agents are forced to juggle two fundamentally incompatible tasks: making high-level semantic decisions and managing a sprawling, unstructured mountain of raw text. As context windows fill up, attention dilutes, and the model starts hallucinating connections or dropping critical evidence entirely. Researchers have found a cleaner way to fix this. The approach is called Harness 1, and it's built around a single architectural insight: cognitive offloading. Instead of forcing the language model to remember everything inside its own context window, they built an external, stateful system to handle the bookkeeping. The model focuses purely on strategic reasoning, while the harness manages the messy details. Think of it like a programmable caseboard. The model acts as the researcher, deciding what to search for, which leads to follow, and when it has enough evidence. But instead of trying to hold every clue in its active memory, it interacts with a structured evidence graph. Every time the harness ingests a document, it doesn't just dump it into the prompt. It parses entities, extracts shared attributes like names, dates, and locations, and builds a dynamic knowledge graph. This graph tracks provenance, flags duplicates, and maps semantic relationships between sources. When the model queries the system, it's not reading a raw text dump. It's querying a structured state that updates in real time, acting as an external memory bank that never hits token limits. But a graph alone isn't enough. You still need to manage token budgets and prevent the model from treating retrieved text as ground truth. That's where the curation pipeline comes in. The model assigns an importance score to each retrieved document based on its current hypothesis. The harness then enforces a strict context budget, automatically promoting high-signal evidence and silently archiving or discarding low-value text. Before the model commits to a document as a key premise, it runs a formal verification step. It explicitly checks whether the retrieved text actually supports its current claim, rather than relying on implicit pattern matching. And to keep things efficient, the harness compresses search results down to the most relevant sentences using a lightweight relevance filter, so the model never gets drowned in noise or forced to guess which paragraph contains the answer. Now, how do you actually train a model to use this kind of structured environment without it cheating? The team used reinforcement learning, but with a carefully designed reward function. They didn't just reward the agent for finding the correct answer. They specifically rewarded tool diversity. The model gets penalized for search spamming and rewarded for actively using the full toolkit: searching, curating, verifying, and reviewing past findings. This reward shaping forces the agent to learn a balanced rhythm of exploration and refinement. It stops treating the harness like a black box search engine and starts treating it like a collaborative research partner, internalizing when to gather more data versus when to synthesize what it already has. The results are striking. Across 8 challenging benchmarks spanning web research, SEC filings, patent analysis, and multi-step reasoning, Harness 1 outperforms existing open-source research agents by a wide margin. But the most important finding isn't just the accuracy score. It's the generalization. When tested on completely unseen domains, the agent actually performed better than on familiar training topics. That tells us something critical. The model isn't memorizing domain-specific patterns or relying on shortcut heuristics. It's learning transferable research strategies. By operating over a structured state, it's internalizing how to systematically gather, verify, and synthesize evidence, regardless of the subject matter. This matters because real-world data isn't clean. It's dense, highly structured, and buried in legal or technical language. If an AI can accurately extract a precise effective date from a financial filing, or verify a drug's medical indication from a regulatory letter, it's proven it can handle high-stakes information retrieval. These documents don't give up their answers easily. They require the model to read full sections instead of relying on short snippets, because context is everything. A single sentence might be ambiguous, but the surrounding regulatory language often contains the exact constraint or exception you're looking for. And because of that, the research behind these systems follows strict validation protocols. Every retrieval, every curation decision, and every verification step is tracked and logged. Researchers verify that the system retrieves the right evidence, that the search strategy is reproducible, and that limitations are clearly documented. This emphasis on traceability and reproducibility is what turns a clever algorithm into a trustworthy tool. What we're seeing here is a fundamental shift in AI development. For years, the industry focused almost exclusively on scaling model size and parameter counts. Harness 1 proves that designing the environment the model operates in is just as critical. By offloading routine state management to a structured harness, we give agents the space to actually reason, verify, and curate evidence like a human researcher. As these systems tackle increasingly complex, real-world tasks, that kind of architectural support might be the difference between an AI that gets lost in the noise and one that actually finds the signal. And that's not just a technical upgrade. It's a necessary step toward AI that we can actually rely on.